All right, hello again, everyone. Today we're going to continue where we left off last time with the simulation. And if you recall, we ended last time with an error, some plugin error, something like that, where the geometry that we prepared was not properly loading into the next model module. And so after some troubleshooting, I was able to determine that the problem wasn't with all the parts that we created. The problem was with the chassis actually. And so I tried like the debugging tactic that I tried was first I unshared all of these. So unshare is just the opposite of share, which we ended with last time. So it unshared it so it wouldn't be transferred to the next module. And so the error still existed, so I knew, okay, the error isn't with these guys, it's with the chassis. So I tried the opposite where I left these guys shared, but I unshared the chassis. And so that's currently what we're looking at. And then I tried opening it up in the next module and everything just worked. This isn't typically what we would be doing to import the chassis, but the chassis is still importing. It's just not organized in like these folders that would be very much preferred. So I'll show you that right now when we open it up. So we hit edit, right click edit, and it's going to open up ANSYS Mechanical, as you can see in the bottom left corner of the screen. I am sharing my screen, right? Yeah, great. So we'll just let that load up. And so yeah, typically I've never seen this problem before. It just has something to do with the particular geometry for FE6. There might be some like incompatibility somewhere. It's kind of hard to pinpoint, but doing this resolved it, just unsharing the chassis, leaving the other ones shared. But yeah, hopefully you won't ever run into this problem. Okay, well now we can see it's all loaded up, the geometry that we left off with. Um, Everything looks exactly like it should. It's all just 2D lines in 3D space, and they're all beam elements with the proper beam profile. And so now if we go into geometry, this is what I was talking about earlier. All of these guys which shared properly are categorized in nice little folders. So they're just going to be a lot easier to work with, as we'll see. Whereas the chassis beams, they're just not organized at all. Let me see if I can make a folder. I can group them. That's very useful. Let's call them chassis beams. Okay, well, that actually solves a lot of things. But anyways, now the next step is we need to define our material. So if you recall, we already, within Workbench engineering data, we added 4130 steel to our engineering data. And so now we have to just select each beam and then just assign it to 4130 steel. And once we do that, we'll see some nice little check marks. And just a quick tip, the fast way that I'm selecting all of these beams rather than control clicking each one is you just click the first one and then hold shift and then click the last one and it'll just select all of them in between. So that's just a helpful tip. So we're just going to go through and define all of our beams as 4130. Almost done. Okay, so now all of our geometry has been defined with a material and it's all been imported correctly. And you can see beautiful little check mark right there next to geometry. And okay, so the next step, we're pretty much almost there. All we need to do next is worry about all our connections. So this includes all the joints and the springs that are going to be that we have to manually define. And there's pretty easy way to, there's a way to make your life easier when it comes to these connections, and I'll show you exactly how to do that. We're actually going to automate it, which is really cool. And then, yeah, we just have to make a quick mesh and apply our boundary conditions and just look at the results. So we're really close to being done. But it could take some time to get used to, which is okay. So yeah, materials, we don't need to worry about this. We already added this material from the workbench engineering data, and cross sections with, these are the cross sections that are being used within the chassis. It's helpful to know. These are the coordinate systems, so it's just the global origin of the chassis, in addition to the two other origins that we defined. And this will come in a bit, why we defined that. And then connections. Okay, so right before we do connections, the step to take in order to make your life easier is defining name selections. So this is what I'm talking about with a name selection. So yeah, let's go ahead and do that first. And so I'm going to go ahead and make all the appropriate name selection folders, and then we'll go through and actually define the name selection. And it'll make sense in a bit. I'm just going to pause the recording while I define all these folders, just to save some time. All right, we're back to recording, and so I've defined all the different name selections that we're going to use. And basically what we're going to be doing now is defining all the points where a joint will be made. And so a joint is made, for example, just looking at this left front corner, we have joints there, 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 there. So at all the A-arm and chassis pickups, and also here at the upright and A-arm pickups. So there's going to be joints there, and we'll go through what types of joints in a bit. But right now, all we need to know is there's going to be joints at, what is that, 6 different points in each front corner. And then in the rear, we have the same 6 with the A-arms and chassis and A-arms and upright. And also we have the push rod and rocker to worry about. So there's a joint there and a joint there. And so that is really what determined the name selections that I made. So the naming convention I'm using is chassis A-arms means the joints that'll go between the chassis and the A-arms, but the node, which is on the chassis. So the first word is what body the node belongs to, and the second word is what that node connects to, if that makes sense. For example, with A-arms chassis, it's going to be the joint on the, it's going to be the node on the A-arm at the point where it connects to the chassis. So this might be a little confusing, but look, I'll show you right now. If we hide the chassis, then so these are all going to be the A-arm chassis nodes that we're interested in. So all of these points connect the A-arms to the chassis. And so we're going to put it in this folder, A-arm chassis name selection. And next, the show. Okay, 1 second. Okay, so now we're going to select the same location, but the nodes will belong to the chassis now. So this one's a little tricky since there's multiple. And it could be useful to make your selection just a vertex, so it won't select like lines, only nodes, which is what we want. Okay, so that's the point. Just gonna have to go around the chassis. Okay, almost done. Perfect. Okay, and now it should make a little bit more sense, the difference between chassis A-arms and A-arms chassis. So the chassis A-arm nodes are these points where the A-arms connect to the chassis, and if we hide this body, and the A-arm chassis points are the points on the A-arms which connect to the chassis. So it's a very subtle difference, but see if we click both of them, they look identical, like because the location is the same, but it's just on two different bodies, and we're going to connect these two, the vertexes on these 2 points with a joint, and we'll go through how to do that in a bit. And I'm just going to pause the video and go through the rest of these. Actually, 1 second. One thing that I did notice while I was making these folders was that we actually made an error in defining the pushrod earlier. So if you look into this corner particularly, we will see that there's quite a lot of things going on. So there's going to be an A-arm and upright pickup, and also a pushrod and upright pickup. And so I've noticed when I've tried to do this in the past that ANSYS kind of gets confused. It's unable to properly define the joints because there's so much going on at this point. So in general, I'd say it's best practice to only have one type of joint at one node. So for this reason, we're going to go back into space claim, or I'll just do that. I'll pause the video and take care of that. And all I'm going to do is delete this line, this pushrod, and just connect it from here to there instead. So this point's going to remain the same, but instead of connecting to the top of this upright, I'm just going to connect it to the middle, which it's not, again, it's not accurate to what it actually is, but for our purposes, it's going to be close enough. So yeah, with that, I'm going to pause the recording and take care of all that. So I'm going to make a new pushrod from here and also go ahead and fill out these folders. So see you in a bit. All right, and we're back. So the changes that I've made are exactly what I was talking about earlier. If we go through, we can see in the rear now we have the pushrod coming from here, this point on the upright rather than this point on the upright, and which is exactly what we want because, again, remember, this point would just get too crowded with multiple joints that ANSYS, in my experience, hasn't been able to handle. And also I've gone through, and once again, just the way I did that process of changing this position was I went back to space claim through geometry. I deleted these lines, I drew new lines, I attached it to the right beam profile, and then I split this pushrod in half as we went over earlier, and then I shared the pushrod. Then when we came back into ANSYS Mechanical, I just had to apply the geometry material to 4130 steel. And then I went through and finished all the name selections. So these are the points on the chassis where the A-arms connect. These are the points on the A-arms that connect to the chassis. This is the point on the upright that connects to the lower A-arms. These are the points on the lower A-arms that connect to the upright. This is the points on the upright that connect to the upper A-arms. Points on the upper A-arms that connect to the upright. Points on the pushrod that connect to the upright. Points on the upright that connect to the pushrod. Points on the pushrod that connect to the rocker, and points on the rocker that connect to the pushrod. That was kind of tedious to go through, but trust me, by doing this, it's going to make our lives a lot easier in this next step that we're about to do. So we're ready to create our joint. So we're going to go to connections, right click, hit insert joint. And let's just go ahead and call it a spherical joint, which means that rotation in the X, Y, and Z axes are free, and but translations are all fixed. And so it's scoping it based on the global coordinate system, which is exactly what we want. And let's just start with a random joint. Let's do the point where the chassis and A-arms connect at the front left bottom of the vehicle. So to do that, let's hide the chassis, hide bodies, and we'll just select this guy. We can call it the reference. Actually, let's call it the mobile. And then when we show the chassis and hide the lower, select that point and call this the reference. Okay. Oh, wait, 1 second. I'm just going to redo that whole process. I think the way I did it was confusing. So we're going to insert a joint. We're going to call it spherical. And so, okay, the way we define a joint is there's a reference and a mobile. So these are really interchangeable. It just means one of the points is on one body and the other point is on the other body. So one would be the chassis point where it connects to the A-arm, and one would be the A-arm point that connects to the chassis. And it really doesn't matter which is which. I haven't found any difference between which is reference, which is mobile, but I'm just going to arbitrarily make the reference equal to the chassis point and the mobile equal to the lower A-arm point, so at the same location. So reference, let's hit chassis, and now let's show the lowers and hide the chassis, and go back to the joint, and see the reference is all done. For mobile, we'll choose that point. And now if you see, there's a nice little check mark right there, meaning that the joint has been defined at that point. And now we can just show all the bodies, and that's the joint right there. Okay, and now this is where you might see, okay, if you manually do all of these joints, there's so many joints. Let's see, 6, 12, 24, and then 25, 26, 27. There's 28 joints. So you could do that all manually, where you just insert joint and do all that. Or we could take advantage of this work that we already did with the name selections and just go ahead and automate it all. So if we go into automation, object generator, it pulls up a little tab on the right side, and we're just going to say, okay, I want to create a joint that looks exactly like this guy, but at different points. So it's going to just duplicate this object at the points that we specify. So first off, let's say, remember the reference was the chassis points where the A-arms connect, and the mobile we said was the A-arm point where the chassis and A-arm connect. So let's just say that the chassis A-arms and then A-arms chassis as we defined earlier. And we'll say, okay, these vertexes need to be within, let's just say 5 millimeters in order for it to create an object there. And really it's like a lot less than 5 millimeters. As we saw, like the points look exactly the same. They're at the same place. So it will work with this tolerance. And scope to adjacent, that's the one that works. And we're going to ignore the original, which means we're going to ignore this one that's already been created and just create, how many is it? 4, 8, 12, 16. So it's just going to ignore one of these and create 15 more. And let's just, in order for us to identify it nicely, we'll just call it chassis A-arms. And then I'll put a space because we'll see why. Okay, so now just generate, and that's it. We have created all 16 joints now with the chassis and A-arms. And I'm also just going to rename this to have the same chassis A-arms. And so yeah, you'll notice I put a space after this word, after arms, because otherwise it would just connect it with the word spherical. That's just a OCD thing, I guess, but okay. So if we go through all of the joints, just arrowing through, we can see the spherical joints have been created at all of the points that we defined. Perfect. So all 16 between the chassis and the A-arms are done. And now we're just going to go ahead, do the same process for the remaining joints. And so we'll just make them all spherical right now, and then we're going to go in and actually look at what boundary conditions are actually correct. Okay, so next up, we'll do the between the upright and the lower, between the lower and upright. So yeah, it doesn't matter which is reference, which is mobile. We're not going to ignore original because we want to create 4 of them. Okay, I don't know how to explain this. So it's ignoring the original would assume like, okay, in this group, we already have made a joint at one of the vertexes. Whereas now we're just using this type of joint in order to define joints here. And so we're not going to ignore an original because this original does not correspond to the new nodes that we're creating, if that makes sense. So yeah. Okay, so now we're just going to call it upright lowers generate. So it should now create 4, right? So 1, 2, 3, and 4. Perfect. And just we're going to repeat the process: upright upper, upper upright, and then call that upper generate. It should create 4 more. Just check them. 1, 2, 3, 4. Beautiful. And then pushrod upright, upright pushrod. Call it pushrod upright. Should just create 2. 1, 2. Perfect. And then pushrod rocker, rocker pushrod. And this should also just create 2. 1, 2. And with that, we're done with the object generator, object generator automation, and we'll see we have all of the joints that we need, which is awesome. Next step, now we have to go through and customize the joints based on boundary conditions. So, okay, in general, the boundary conditions that I've been using is that we're going to have spherical joints at the chassis and the A-arm, which is done. All 16 of these are all good. And then we're going to also have spherical joints at the A-arm and upright, upper. So these upper ones are all good. And we're also going to have spherical joints at the rocker points. So the pushrod rocker. I just noticed the naming is kind of weird. But okay, that's fine. At least the beginning words are right. Okay, anyways, so the uppers are good, and then the rockers are also good. And with the pushrod and the upright lowers, those are the only ones we need to customize. So that's going to be these 4, and also these 2. So, okay, you can see all 6 that we're going to have to customize. So yeah, again, these 4 are going to be different, and these 2 are going to be different. And so now how do we figure out what they're going to be? So I've been referencing a paper. We have it on our Google Drive if you're on the team. but it's just this paper. It's an FSAE technical paper. And so based on this paper, the very minimum boundary conditions to solve a torsional stiffness, to constrain a torsional stiffness simulation, or in real life, this is for a real jig, are these conditions. So it's spherical in the on the right side completely for the okay, first, all the uppers, these are the uprights, and all the uppers where it connects to the A-arms are spherical, as I already told you guys, and also the lower uprights on the right side are also spherical. So those two are also taken care of. Then all we need to do is put a fixed, so no rotations on the left rear and only rotations about the y-axis on the left front. And so this is the very minimum conditions, but with like some trial and error in my previous simulations, I've noticed that this minimum setup would not solve. And so if you read below, it says that there are alternate constraint setups to all of these, and the results indicate that the difference for all the cases is less than 0.25% from the minimum setup. So it's very little error if you introduce more constraints. So with that, I did introduce a couple more constraints. I think I went up to case 3 or 4. I don't remember exactly right now. But with that, so I'll show you what that looks like. So if we go to this corner, remember it was completely fixed. So we're just going to change this guy to a fixed joint. And so now you'll notice that all of these are gray, which means there's no rotation, no translation allowed at this joint. And then we're going to apply to both of these corners only freedom in the y direction. So for rotation about the y. And so for that, we're going to create a general joint where we just have more customization. We want to free the y direction. And also for this guy, we're going to say the same general where we free the y. Okay, and with that, now we have free rotation in the y at this point, fixed at this point, free rotation in the y at this point, and spherical right here. And now the last thing that I talked about, okay, so actually let's go back to the paper. And so we have, so there's the minimum constraint setup, then there's the minimum constraint setup with fixed X and Z rotation at the base of the right rear post. So that's what we did. We fixed X and Z and we left Y free. So actually, yeah, this is the alternate constraint setup that I have incorporated. I just went up to case 2 and added an additional X and Z rotation fixed constraint to the right rear bottom upright. It's a lot of words, yeah. So, okay, now last thing we need to do is go to the push rod and upright. And again, we're just gonna make it a general joint where we fix, or where we free only the X. And same thing for this. Go general and free X. So, okay, the reason for that is if you look, we're basically saying, okay, we just want the upright to rotate about this axis, which, I'm sorry, the push rod to rotate about this axis, which is exactly what we want. And so you might notice, okay, it's not exactly aligned with our axis. Like there's a slight difference in angle, very subtle. Actually, I don't know. Yeah, okay, very slight difference in angle between this upright, between this push rod, I'm sorry, and our coordinate system. But it's so slight that I neglect that and we just still scope it based on the global coordinate system. Yeah, I hope that makes sense. Whereas for the upright, whereas for the rocker, there's quite a large angle difference from the global coordinate system, which is why we actually defined our extra origins right here, origin and origin 1. And we'll see where we incorporate that next. So it would be nice if we could just say, okay, scope it to this new coordinate system and make only rotations about like the X or something in this new coordinate system, local coordinate system, only free some rotation based on this local coordinate system. So unfortunately, I've tried it a couple times, but I wasn't able to get it to work with the joint definition here. But the way I got around it was with the actual boundary conditions for the simulation, we can add a remote displacement constraint, which causes it to behave exactly how we want it. But okay, before we get there, now we have all of our joints defined properly. Yeah, all the joints are defined properly and we're nearly done with the connections. The only thing that's left is to add some springs. So we're going to add 4 springs. You can also do this with the name selection, like object generation automation. But I found it's just 4 of them, so it's not too bad. And so the very first one is, we're going to just go from here to about there. And then again, another one we're going to do from here to there. And then last one, we're going to do, or if not last one, second to last one, we're going to do it from there to, I believe it was this node. No, it was this node. That's right. And then from here to this node. Perfect. So this is what our springs will look like. The rear is more accurate just because it has the whole rocker pushrod shock interaction. And then the front, it's a little bit less accurate, but so I talked to the suspension lead and I learned that just looking at the load path from where the pushrod and rocker and shock would interact, it doesn't, it's only, the rocker is mainly used in the front for clearance issues, whereas the rocker in the rear is actually just to change the load path. So it goes, like the rocker actually affects the load path significantly in the rear, opposed to the way it behaves in the front. So it's an okay assumption to just make it essentially direct acting in the front. And also another thing is, though joints get confused in ANSYS, if there's multiple joints, if there's a, so yeah, joints get confused in ANSYS if there's, for example, if instead of this spring, it was a beam, ANSYS would just not be able to compute this corner just because there's a joint between the upright and A-arms and also between the push rod and upright. I mentioned this before too. But now that we have a spring rather than a beam, it's able to deal with this corner just fine. So that's one of the main reasons that I've chosen to use springs within ANSYS. And so you'll notice there's no check marks here yet. And the reason for that is we haven't defined a stiffness or a damping value. And so the value I've been using is just a very, very, very large number, just to be as close as possible to a rigid beam. And I've noticed that if I increase even more than this, like if I tried 1 times 10 to the 5th. So like, what is it right now? 20,000. So I tried 100,000 and it didn't change results very significantly. And then damping, we're not going to worry about damping right now, just because we're mainly interested in the stiffness of the vehicle, not really the like transient damping response of it. But yeah, okay, with that, we have our connection. Everything is all done. Let's go ahead and mesh. We're gonna, personal preference, I learned how to do sizing. So I'm just gonna select all the members on the chassis, all the bodies, and then yeah, just control click to continue to select. And you just have to be a little careful to make sure you get everything. We just want everything to be green. Okay, let me just pause recording. This might take a minute or two. Okay, we're back. I just found a really quick way to do it rather than selecting it and falling to human error. You can just go here, make sure you're in this selection filter, then just hit Control A and it selects everything. So yeah, now default size, which is set to 50 millimeters, and see what this mesh looks like. And yeah, 50 millimeters would probably be a pretty coarse mesh, but I think it's fine to start with. Just yeah, while we're setting the simulation up initially. Actually, it could be quite fine relatively, because it's taking a while. We'll see. Yeah, that's pretty coarse actually. We could make it a little more coarse just to do some quick sims. I think I'm gonna do that. Make it 75. Generate the mesh. All right, this should probably be good. And so now we just have to apply our boundary conditions and run the sim, and fingers crossed it solved on the first time. So, okay, there's a couple of things we need to add. Easy things first. Let's add our forces. So we're just going to apply a couple. Excuse me. Sorry about that. So yeah, we're going to apply a force couple to the front upright. So basically a upward force here, downwards force here, and that's basically a torque about the center. So we're going to apply it to the upright edges, there and there. And let's say the location of the force will be right there. And we'll apply 1,000 newtons vertically. And same thing on the right side of the vehicle. We're gonna put the location down here and change this to component and -1,000. So now you can see there's a force couple at the uprights. That's it for the force. Now there's quite a lot of details with the fixtures, but we'll go through each one carefully. First one, remote displacement. We want to apply it to these corners. And this is just, we're just going to say, okay, we don't want it to translate in the X direction. So we'll just fix that. And the location at about which this remote displacement happens, doesn't really matter in this case, but we can see, so about this point, there's going to be 0 x direction translation. And this might just be like a redundant boundary condition, but I like applying it just so I know what I'm doing at each corner. And so basically, we don't want this guy to move this direction, in the x direction. Okay, next up, another remote displacement. In this case, we're going to, for the upright rear, we're going to fix all translation. So at this point, we want to have no XYZ translation and also no rotation. So if you recall from the paper that we were referencing, this point is completely fixed as the boundary condition, and the point at which, we want 0 translation and rotation about pretty much any point on the vehicle. Right now, the point is just right there, which it doesn't, again, matter too much in this case. It will matter when we get to the rockers. So one more remote displacement, this time on this corner. We're just going to say no XYZ translation, but rotations are completely allowed. Okay, and then now the very last 2 remote displacements are, so we have 2 more, which is going to be for the rocker. So if you recall earlier, we just defined this rocker point to be a spherical joint. So free rotation with this joint, but that's not actually the way the rocker behaves. It's actually going to, if we select that point, it's going to only rotate in a particular direction like this. It's hard to illustrate with a mouse, but okay, let's choose our proper origin. So we only want this rocker to rotate about the y axis with this local origin. Let me just get a better view. Okay, so here's the rocker, this beam right here, and we only want it to rotate about the y axis. And the rotation will be about the midpoint. So, and we'll say free y, or basically fix x and z, and fix x and y. So what I've applied here is we're allowing rotation about this center point based on this coordinate system about the y-axis, and we're allowing translation about the z-axis. So it's allowed to move in this z direction. It's allowed to translate like that about this origin, and it's allowed to rotate about the y-axis about this point. So this point is allowed to rotate and translate in the y and z respectively about this point. Hopefully that makes sense. And lastly, we're going to do the same thing over here on the right side of the vehicle. And the location is the midpoint. And fix x and y translation. And fix x and z rotation about this origin. Everything looks good. And now the final boundary condition that we're going to apply is inertia relief. So I just changed it from off to on. And you can read about this online. There's a couple like good forum posts about in ANSYS that describe this condition. But the way I understand it is it basically allows the body, it allows us to analyze the chassis at a local level, ignoring the like global effects of it. So what that means is, like, if I apply a force here, um, it is very possible that the entire chassis just moves upwards, and we don't really see the chassis twisting at a local level. It just displaces like crazy due to the very little boundary conditions that we've applied. So with this inertia relief, it basically says the entire body is not going to really move around in space, but we will still see the local effects that we're interested in. So hopefully that kind of makes sense. I do recommend looking up that boundary condition online. It's very helpful. So now we're just going to insert what we're looking for with the results. We'll just do normal total deformation, and fingers crossed, let's hope this solves. Yeah, it's very possible that this could fail. It might solve on the first time. Okay, yeah. It usually doesn't solve on the first time. There's going to be some debugging that we're going to have to do. I'm going to actually go ahead and do some of that debugging right now, and then I'll come back and report what I found. See you in a bit. All right, yeah, so I've been trying to debug for a while. Haven't found the right solution yet. I've been trying a couple different things. One of the things that I know I did wrong earlier was the way I defined the rocker. So I looked back at an older sim, and rather than us applying a remote displacement about this point, it's better to do it about the entire rocker. So the entire rocker is free to rotate about the y-axis of this local coordinate system about this point. And yeah, so that's just one thing that I fixed for both rockers. So it's an edge rather than a point. And so yeah, I'm going to keep debugging over the next few days or so, and I'll finish up the last part of the video, and we can go over the whole torsion calculation also. But yeah, in general, the process that has been covered thus far is the entire process. Debugging will just come with experience. I know I still struggle with it, but yeah, hope you were able to gain a lot from these videos. And yeah, I'll see you next time. Thank you.